Okay, so today we're going to be looking at an introduction to vectors. So, we've all seen before that vectors are quantities that have both a magnitude and a direction. So the difference between a vector and a scalar is that a vector quantity is a quantity that has both magnitude, that is its size, and direction, that's the direction it's facing. A scalar quantity is a quantity that has magnitude, like 3 or 4 or something random, the square root of 5, but no direction. So we're going to have a go. I'm going to have a look through these and highlight which ones are vectors and which ones are scalars. So the vectors volume. Volume doesn't have direction. So my vectors are velocity, acceleration, that one there, 10 kilometres, that's magnitude on a bearing of 75 degrees, that's our direction. A pass in soccer would have a direction and it would also have a speed. Rotation of 180 has direction but no magnitude. Force has direction and magnitude, as does height and displacement. Now distance and speed, they don't have direction. If I say I've gone 10 metres, it doesn't imply a distance of 10 metres, it doesn't imply the direction I've gone in. Same as speed. So velocity, which is a vector, is a scalar, which is speed. And displacement as a scalar is distance. Okay, so vectors are used everywhere in maths, and it's going to be key to other topics that we're doing later on, such as projectile motion, and even in differential equations when we learn about differential fields. So vectors are mostly used in the real world. You'll see them on the news, so if you see maps of climate and weather, vectors will be shown as the direction and strength of wind. Imaginary numbers, so our complex numbers of vectors, they have both a real and an imaginary component. Okay, some terminology. So we've done scalar and vector. We actually might come back to these. We're going to do a lesson basically on each of these different types of ideas. Something important that we're going to come to soon is a unit vector, and it's a vector which has a length of 1. So a vector tells us how to move from one position to another. So for example, if I'm moving this piano 3 meters to the right, the vector is 3 to the right. So we can see everywhere on that piano has been moved 3 meters to the right. Now we've actually seen vectors before in functions, so in advanced functions and our extension 1 functions. So if fk is translated, y is fk by k in the x direction, it has equation y is f minus k, and we would say it's represented by the translation vector. Now we're going to learn about this notation soon, but it has a translation vector of k0. It's moved k in the x direction and nothing in the y direction. Similarly, if we were moving something up by k, so y is f of x plus k, we would say it has a translation vector of 0k, it's moved up. Now we represent a vector as an arrow. The arrow always points in the direction the vector is going in, and the length of the arrow is important. This particular vector can be written in vector column notation. So we would say this is vector. If we called it, say, P, this would be vector P. We put a little squiggly line. Again, we're going to get to that notation in a second. Vector P is the vector UV. So U is the X and V is the Y. It's almost like combinatorics. In fact, it's the same notation, except importantly, they have nothing to do with each other. We can also write them as an ordered pair, U comma V, although we rarely write vectors like that. Specifically, this is the vector. We're going across 1, 2, 3, 4, 5, 6, 7, and going up 1, 2, 3, 4. So it's the vector 7, 4. Okay, displacement vectors. So we can see these arrows, they're all of the same length, and they actually represent the same thing. So all of these arrows represent the same vector. They are parallel and equivalent. They all represent the vector, and the same vector as before, 7, 4. They all represent the same vector. We call these displacement vectors. Now, if B and C are 2 points on a grid, there is a unique translation that takes you from B to C, and that's represented by the arrow starting at B and ending at C, and we say that's a vector BC with an arrow on the top. We draw it like this, not a highlighter. We draw it like this, BC with an arrow on the top. The arrow is important. It's telling us we start at B and go to C. Now, translation isn't unique. What that means is if I have a vector and I move it anywhere on the Cartesian plane, it is still the same vector. So here we've got vectors B and C, BC and DE. They are both the same vector, even though they're at different positions on our Cartesian plane. In saying that, one special displacement vector is the position vector. It is the vector from the origin to point A, for example. So we can see in this diagram that vector OA is the same as vector BC, and it's the same as vector DE. So we say these vectors are parallel and equivalent, or they're the same vector. However, the vector OA is the position vector of the point A because it starts at the origin, whilst BC and DE are displacement vectors. Now, there's many different ways that we can position and name vectors. Of course, we've seen BC with an arrow on the top. We also, and I talked about this before, have a letter with a lowercase letter with a squiggly line under it, and also in text bold letters, but obviously we can't write in bold, so we put a little line at the bottom. So we're going to sketch some vectors. So vector representing the point 4, 7. We're going across from 4 and up to 7. We go up here, and we put a line on it. Part B minus 3 minus 5 would be down here. We put a line on that. Part C, 4 minus 4, would be down here. And we put an arrow on the end because vectors have direction. Minus 2, 6 would be up here. All right. Unit vectors. So we talked about this briefly in our definition. So a unit vector is a vector with length 1. Now, there are lots, and there's an infinite amount of unit vectors, but two particular important unit vectors are I and J. In extension 2, we have a third one called K, which is in the Z direction. So, a unit vector is a vector of length 1. Now, the vector of length 1, which is a vector 1, 0, so straight across the x-axis over to x equals 1, is what we call I. It's what we call one of the standard unit vectors. Similarly, if we go up in the y direction by 1, we call that J. So for the diagram above, we can use column vectors notation to write I is 1, 0 and J is 0, 1. So therefore, the vector 3, 4 can be written as 3i plus 4j. Importantly, these i's and j's are not pronumerals. We can't add them, we can't substitute things for them, they're vectors. So we can never plus I with j. So write these in column component form. It's minus 3, that's a highlighter again, minus 3i plus 4j. Here we've got 0i minus 2j, which we would just say minus 2j. And we've got minus 6i minus j. Going back the other way, 12 minus 4i, 12i minus 4j would be 12 minus 4. This would be minus 7, 0. There's no j component. And this would be minus 5, 3. Okay, parallel and equivalent vectors. Two vectors are parallel if they have the same direction, that's obvious, but not necessarily equal in length. Now, two vectors are equivalent if they have the same direction and length. So here we can see A and B are parallel, but they're not the same length. But we can see A and C are both parallel and equivalent. So we say if a vector is parallel and equivalent, they are both the same vector. Something that might be obvious to say, vectors on top of each other are parallel. So A and B are parallel to each other, but they're not equivalent because they're not the same length. We're going to come back to this terminology later when we learn about all these different laws. Okay, multiplication by a scalar. When a vector is multiplied by a scalar, now a scalar is just some number. It's not a vector, it's a number like 2 or 3 or a half or square root of 5. It's a number. So when a vector is multiplied by a scalar, its length is multiplied by this number, but its direction is unchanged, unless the scalar is negative, in which case the direction is reversed. So here we can see we've got the vector A and the vector 2A. So multiplying the vector A by 2 just increases its length by 2. If I multiply the vector A by minus 1, it's the same vector except it's facing the opposite direction. So negative vectors. The vector minus A has the same magnitude as the vector A, but in the opposite direction. So here we can see we've got the vector AB and then the vector BA. So this is the vector AB. And the reason we say AB is because, and not BA, is because we can see the arrow is starting at A and going to B. This second vector here technically is minus AB, but we would prefer to express that as BA. It starts at B and goes to A. Last thing for today, the zero vector. We define the zero vector in 2 dimensions to be 0 or 0i plus 0j, and that's equal to 0, 0. It seems like it's pretty pointless to say, but this segment represents a line of length 0 and no direction, but something that's important for later on is the zero vector is parallel to all vectors. Okay, hope that makes sense. Thank you.